Okay, this is the notes for Section 1.1, Language of Algebra. Section 1.1, to begin with, has a lot of, first of all, a lot of review from your Algebra 1 course, but also a lot of vocabulary that is going to be pertinent as we move through this entire course. I picked out 4 vocabulary terms that you're going to need to get down in your notes that are going to become fairly important as we move through. The first is variable, then expression, equation, and then finally formula. A variable, and all 4 of these should be somewhat familiar to you from your earlier algebra course, but just to review, a variable is a symbol that can be replaced by any one of a set of numbers or other objects. So examples of that would be something like 3x, where x would be that variable, or 2y plus 7, where y is your variable. An expression is a combination of numbers, variables, or operations. So both the examples that I had above, 3x and 2y plus 7, those would be examples of expressions, where you have numbers, variables, and operations. So when I have the expression 3x, that means 3 times x. Although there isn't an operation symbol there, it's implied that there is an operation symbol. The third term, equation, is a sentence stating that 2 expressions are equal. So when we talk about algebra, we're really learning a language, okay? And the sentence of this language is an equation. So if I say something to the effect of 2x plus 8 equals 15x minus 9, that's an example of an equation or a sentence in algebra. Okay? And the fourth and last term that I want to talk about right now is the idea of a formula. And a formula is a sentence stating that a single variable is equal to an expression with one or more different variables. Now, you've encountered a number of formulas either last year in geometry or also in algebra a couple of years ago. But an example of a formula would be the area of a rectangle is equal to the length of that rectangle times the width of that rectangle. We have one variable, a, for area, is equal to more than the product or the sum or any amount of operations involving one or more other variables, in this case length and width. Okay, at this point, you might want to just take a minute to, if it's been a while since you've read 1.1, you might want to just take a minute, pause the video, and take a look at example 1 in your reading, and then start it up once again once you've reread that. But I'm going to now go through example 1 here. It says, Maria collects stamps. She already has 860 stamps in her collection. She plans to buy 20 stamps each month. How many stamps will Maria have after M months? Okay, we're looking to write an expression here. A lot of times we can write expressions or mathematical sentences to model real-world situations. To do that here, we're going to look at the information we have. We know we're talking about M months. Well, that's going to be the variable that we're going to use in our expression. We know that we start out with 860 stamps, and we know that each month we're adding 20 additional stamps. So when I write my expression, I'm going to write it as, here's what I'm starting with, 860. Each month I'm adding to it 20 stamps. Well, to figure out that each month, I'm going to take 20 times the number of months. So after 1 month, we'll add 20 onto 860. After 10 months, we're going to add 200 onto 860. So this expression would model this situation. Okay, one of the things that you're going to be asked to do quite a bit in Chapter 1 here is the idea of evaluating expressions and formulas. The term evaluating means if we're going to evaluate an expression, it's the process of substituting numbers for variables in an expression and calculating the result. Something that you did quite a bit of in your first algebra course. And it's really something that we have to make sure that we're able to do still at this point. So what I want to do is I want to first review, when we do that, those rules for the order of operations. And according to our order of operations, we're always going to do, if you remember PEMDAS, we're going to perform anything inside of parentheses or grouping symbols first. And then within that, we're going to take powers from left to right, multiplication and division from left to right, and addition and subtraction from left to right. So that's kind of the order in which we're going to do things, and is going to become pertinent as we walk through each of these different types of problems. So let's take a look at example 2 here. Then it says find the value of this expression here when A is 5 and B is 6 and C is 4, which means that we're going to evaluate that expression. So we're going to plug in these values into this expression. So I'm going to rewrite it right now with those values in there. So instead of A squared and C squared here, we're going to put in 5 squared minus 4 squared plus, instead of C, I'm going to put a 4. And here we would have B squared, which would be 6 squared minus 5 squared plus 4 squared. Okay? Now we need to simplify the stuff underneath the radical. And to do that, I have the square root of 25 minus 16 plus 4 plus the square root of 36 minus 25 plus 16. Okay? This is equal to 9. Just simplifying the stuff underneath the square roots, because according to my order of operations, it's a grouping symbol. I have to do that first. Now this is 36 minus 25, which is 11 plus 16. And 11 plus 16 is 27. So this works out real nice, however, this doesn't. Well, the square root of 9, I can simplify that. That's going to be just 3. So I'm left with 3 plus 4 plus the square root of 27. Now I can get an approximation to this. Okay? We're going to talk a lot more about approximations and exact values as we move through this course. You talked a little bit about it last year in geometry. But I'm going to actually leave the square root of 27 just as it is, and I'm not going to simplify that any further. So I'm going to go 3 plus 4, which is 7, and leave my answer as 7 plus the square root of 27. And this is an exact value for this expression. At this point, if you could just pause the video, and for some practice, I'd like you to do guided examples 2 and 3, and then I'll go over the answers here in just a second. Okay, so here's the answers to the first part of guided example 2. You'll notice that for negative b, I'm going to substitute in a 1. For b squared, where you see b, I'm going to put in negative 1. Okay, so all of not just 1, but negative 1 is going to be squared. And then for the other two, this is a 3, a negative 4 here. And then down here we would have a 3. So if we look at step 2 then, the 3 question marks would be 1. So here would be 49, so underneath the square root we would end up with 49. And then this question mark here, where a is, since a is 3, we're going to plug that in for that question mark right there. So if we look at step 3 then, the top value is going to be negative 6, and the bottom value is 6. And negative 6 over 6 would be negative 1. Therefore, when we evaluate that entire expression, we would end up with negative 1. If we look at guided example number 3, it says a kilowatt hour is 1 kilowatt of power used for 1 hour. What does it cost to have a 60-watt bulb turned on for 33 hours at a cost of $9.53 per kilowatt hour? So that's part A. So if I look at part A, to do that, I'm going to say that the cost is going to be equal to 60 watts times the number of hours, which we found out was 33, times the cost per hour, which we know is 9.53 cents. So I'm plugging those values in. Okay? So you need to change 60 watts to kilowatts. Since one kilowatt would be equal to 1,000 watts, we can say 1 is equal to 1 over 1,000. This is the fraction for a conversion factor. Okay? So here's what we have then. 60 times 1 over 1,000, that would be equal to 6 over 100, or 0.06. Okay? Now if we figure out our cost, then it's going to be 0.06 times 33 times 9.53. So if we do that multiplication and division, we end up with 18.87 kilowatt hour cents per kilowatts minus hours. So we're performing those operations on the units just as if they were numbers. In other words, it would be 18.87 cents. In part B, it says let P equal the number of watts in the bulb. Let T equal the number of hours. Let U equal the unit cost in cents per kilowatt hours. Well, then to find that cost, I'm going to take P times T times U and divide it by 1,000. Okay, this is the notes for sections 1, 2. The title of the section is Relations and Functions. At this time, you should have read section 1, 2. You'll notice that in section 1, 2 that there's quite a bit of vocabulary, just like section 1, 1. I just want to highlight a few of them and make sure you get this down in your notes as well. First of all, we have a relation. Anytime you have a set of ordered pairs, or anytime you have two numbers that are paired together, we say that that's a relation. Okay, so like a relationship. Those two numbers are somehow related to each other. Okay. Next term is one of the most important terms that we're going to learn in this chapter, and that's function. I'm going to give you two different definitions of it. They mean the same thing, just different ways of stating it. The first is a function is a set of ordered pairs x, y, in which each first component, x, of a pair is paired with exactly one second component of y. In other words, when you look at a function, the x value can only be paired with one y value. So you can have, if you look at a set of ordered pairs, you could have one of your ordered pairs could be 1, 2. But if that's the case, you cannot have any other ordered pairs with 1 as the x-coordinate. 1 can only be paired with 2 if it's part of that function. So the y value can repeat, but the x value cannot repeat. A second definition of a function is a relation in which no two ordered pairs have the same first component x. So that's what I was kind of getting at as we were looking at number 1 there, and that is, if it's a function, the first coordinate, or the x values, or the first component of the ordered pair, the x values, cannot repeat. Okay. A couple other terms: dependent variable and independent variable. When we have a function, we're going to have two variables. The dependent variable is a variable whose value always depends on the value or values of other variables. And the independent variable is a variable upon whose value other variables depend. Okay? So if I have something, for instance, y equals 3x plus 5, the value of y is dependent upon what the value of x is. Okay? That's what it means for it to be dependent. So therefore, in that scenario, y would be dependent. An independent variable is the exact opposite of that. The independent variable is a variable upon whose value other variables depend on. So in my scenario, x then would be the independent variable. When you think about dependent, the dependent is also the output. If you think about what a function is, the dependent variable, or the output variable, is a function of the independent variable, or the input variable. Okay? So a lot of times we'll say y is a function of x, but it's always the dependent is a function of the independent. Okay, so here's a couple examples I'd like to take a look at. Number one says two angles of an isosceles triangle have the same measure x. The measure of the third angle is y. This relationship can be modeled with the equation y equals 180 minus 2x. So I've got that circled here. Which of x or y is the dependent variable and which is the independent variable? Explain your answer. Okay, so as I look at that, I'm asking myself the question, which one depends upon the other one? And as you look at the equation, y, the value of y, depends on what x is. As x changes, y is going to change. So we say that y is the dependent variable and therefore x is the independent variable. X is the variable that y depends upon, therefore x is independent. Okay? So we can say that y is, for each value of x, there's exactly one value of y. No matter what value I put in for x, there's going to be that exact same y value will always come out. So for instance, if I put 2 in for x, no matter who does it, if they do the math behind it correctly, no matter what, if x is 2, y is going to be 176, 180 minus 4. So this is a function where x is independent and y is dependent. Let's take a look at number 2. It says the average annual price P of crude oil per barrel in the year Y is given by the following table. Is Y a function of P, Y or Y not? And then part B is P a function of Y, Y or Y not? Okay. Well, here's what we want to think about when we're asking that question, when we look at it in kind of that table form, is how can I determine whether or not that's a function? And what I'm going to do is I'm going to look at the table and I'm going to look to see if something repeats. Okay? Well, if I look at my y values, they do not repeat. They are all unique, which means that y certainly can be the independent variable. However, if I look at p and I look at that, it does repeat. It has two 1675s here. Therefore, it cannot be the independent variable. Okay? So I know that y has to be the independent variable, therefore p would have to be the dependent variable. So if I look at part A, it says, is y a function of p? Remember, it's dependent is a function of independent. Well, I know that this has to be my dependent variable, and this has to be my independent variable, because these do not repeat and these do repeat. Therefore, is y a function of p? The answer to that is no, because each value of p does not have one value of y paired with it. Okay, 1675 is paired with 1993, and it's paired with 1995, therefore it cannot be the independent variable. Okay? However, if I turn that around and say, is p a function of y, the answer to that is yes, because as I look at my table now, all of the values that are in this column are unique, therefore there's no repeats, therefore it can be a function. So the answer here is yes, because y has a unique value of p paired with it. Okay? Y does not repeat. Okay, so in section 1.2 we looked at what a function was. Now we're going to look at a different way that we can notate or write functions. We're going to be looking at what we call f of x notation or function notation, which I have written right here. And that's a notation used to describe functions, which we read it as f of x. So when I see something like this, we read that as f of x. The first letter or phrase names the function, and the variable in parentheses is the independent variable for the function, or also called the argument of the function. This is also referred to as Euler's notation. Okay? So function notation, Euler's notation, those two things mean the same thing. That x, or whatever is in the parentheses, that just tells you what the independent variable is in the function. The f is just naming the function. It doesn't have to be f. It could be g, it could be h, it could be m, it could be hornets, it could be Dinah, it could be anything. Okay? It just names the function. Okay? So when we do that, the f of x basically takes the place of the dependent variable. Okay? So function notation takes the place of the dependent variable in a function and therefore represents the second component of the ordered pair. For example, if we have y equals 3h plus 2, that can be written in function notation as e of h equals 3h plus 2. So let's take a look at some examples of function notation here. So I have two examples here. We have g of m is the function with the name g and an independent variable of m. Edina of h is the function with a name of Edina and an independent variable of h. So whatever is first outside of the parentheses, that's the name. Whatever is inside the parentheses, that's the independent variable. So if I look at this example 1, it says t of f, that's how we read that, remember, is equal to 5/9 times the quantity f minus 32. Evaluate t of 86. Well, if I'm going to evaluate t of 86, what that tells me is that I want to put into my function where f is, I'm going to put in 86. So t of 86 is equal to 5/9 times, instead of f, I'm going to put in 86 minus 32. So if we plug that into our calculator, we can go to our calculator here and put in 5/9 times 86 minus 32. If you have forgotten, in terms of making a fraction, you do control and divide. Okay, and I'm going to hit enter on that, and you'll notice that we get 30 on that. So back over here, and let's put our answer then. So the answer here would be 30. So when f is 86, t of f is 30. So you can think of that as being an ordered pair, 86, 30. Okay? Now, a second type of notation that we look at that goes along with function notation is what we call mapping notation. And mapping notation is just another way to express a function similar to the way we would express something in function notation. We can use a colon after the name of the function and an arrow to show the mapping. Therefore, mapping notation for y equals 2x plus 6 can be written as m colon, where m is the name of the function, m colon x is paired with, or m maps x onto 2x plus 6. Okay? So generally when we read that, once again, we're going to read it like this. The function m maps x onto 2x plus 6. Okay? So that's what we call when we say something's called mapping notation. So as we look at number 2 here, it says let f, the function f, map x onto x plus x squared over 20, Evaluate f of 10 and f of s plus f of 10. Well, f of 10 is just plugging 10 in here every place that I see an x. So each one of these x's, I'm going to put a 10 in instead. So f of 10, or f maps 10 onto 10 plus 10 squared over 20. Well, 10 squared is 100. 100 divided by 20 is 5. 10 plus 5 is 15. So f of 10 would be 15. And then if I have f of s plus f of 10, well, we know f of 10 is 15. And f of s is just taking x out in each one of these places and replacing it with s. So that would be s plus s squared over 10. So if I'm going to add those two together, this is what I would end up with. So this is the notes for section 1.4, graphs of functions. At this point you should have read section 1.4 already before starting these notes. The first thing that we're looking at is the idea of domain and range of a function. We've talked about what a function is. Now we're looking at particular parts of a function. When we talk about the domain of a function, it's the set of allowable values for the independent variable. So any number, so if you have, for instance, a function, and remember we can write functions in a lot of different ways. We can write them as ordered pairs, we can write them as equations, we can graph them. There's a lot of different things we can do with functions. But if I have, for instance, an equation of y equals, say, 3 over x, okay? As I look at that function, the domain is all the numbers that I can put in for x. Anything that can go in there. So as I think about my domain, well, almost every number goes in there. There's only one number that causes a problem, and that's 0. And usually when I'm looking at the domain of a function, instead of wondering about what it is, I'm going to wonder about what it isn't. What is going to cause me a problem if I plug it in there? And obviously if I put 0 in for x, I'm dividing by 0, and we know that that's something that we can't do. So the domain of the function is the numbers that I can put in for that independent variable. The range of a function is the set of values for the dependent variable that can result from any substitution for the independent variable. So when you've established what your domain is, the range is the values that can come out of the function. What are the values that I could get for y, or the dependent variable? Okay. Well, in this particular case, you know, if as y gets, I think about it in terms of my independent variable, as x gets really, really big, this whole function, 3 over x, becomes extremely small, or extremely close to 0. Okay. And we could do the same thing if x is negative. Okay. It's going to get extremely small on the negative side. If x becomes extremely small, this function actually gets extremely big. So whether it be positive or negative, it could get bigger on either side of 0. So really, the values I can get for y is every possible value, except for 1. The only thing that I can't get is 0. There's no value I can plug in for x that will give me a 0 for y. Therefore, we would say the range of this function is all real values except for 0. And the domain in this case would be exactly the same. All real values except for 0. How to determine the domain and range of the functions for different forms. So we've got ordered pairs, we've got tables, etc. How do we determine whether what the domain and range is of a function in a particular form? So let's just kind of go through them one at a time. The first is ordered pairs. So if I think about ordered pairs, the domain will always be the first coordinate, or the values of x. Whatever the first coordinates are, or the values of x, will be the domain of that function. And the range of that function will always be the second coordinates, or the values of the y. Okay? So if I look at this example, what is the domain and range of this particular function? The domain will be all of the x values. So 3, 1, -2, 6, and -1. So using set builder notation, we can say that the domain is the set of x such that values are 3, 1, -2, 6, and -1. So when we're looking at it in terms of ordered pairs, it's going to be a finite set of values. In other words, a specific number of values. In this case, there are a total of 5 values that would be part of the domain. Okay? So that's my domain there. Okay? The range is going to be all the y values. So using set builder notation for that, it's y such that 2, 5, notice I don't write 5 twice even though there's 2 5s, 1, and 0. That would represent the y values, or the range of that function. Okay? When we look at it in terms of tables, okay, the idea is very similar. So if the independent and the dependent variable are not given when looking at a function in a table, it is assumed that the left column or the first row is the independent variable. Okay? Sometimes we'll say, you'll give it a table and say which one is the independent one and which one's the dependent one. Other times, if they don't, we can assume that the left column or the first row is the independent variable. The right column then, or the second row, would be the dependent variable. So if I say, what is the domain and range of these given functions? Well, the domain here would be these values for this one, and for this one, it would be these values. So in terms of set builder notation domain, I'm going to do it for both of these. It's a set of values m such that we have 20, 30, 40, 50, and 60. And for this other values for x, it would be 1, -2, 4, and 5. And in terms of the range for these two functions, would be the values of n such that we have -2, 0, 4, 6, and 8. And the same thing would apply for this one. So all values of y such that they are equal to 3 or 2. Okay? Okay, so graphs, the domain is the value of the graph's horizontal axis and the range is the value of the vertical axis. So what is the domain and range of the given function? So as I look at this function p of x, if I look at it horizontally, that's going to give me the domain. So the domain here is the values, if I'm going horizontally, it's going from right here to right here. Or in other words, from -3 to 4. So the way I'm going to write that, once again, I'm going to use that set builder notation, and I'm going to say the values of x such that -3 is less than or equal to x is less than or equal to 4. So with graphs now, it's not going to be a finite set of values. It's going to be an infinite set, and it's going to be all values between those two numbers. Okay? As I look at the range graphically, it's going to be the values, so I'm looking at it from a vertical standpoint. So the lowest point vertically is right here. The highest point vertically is right here. So it goes from 2 to 5. So I can say the set of values of y is such that 2 is less than or equal to y is less than or equal to 5. So that would represent the range of values. Okay, finally we're going to look at equations and how we can look at domain and range from that vantage point. The domain is the set of numbers that can be substituted for the independent variable, and the range is the set of numbers that can be substituted for the dependent variable. So when I look at this equation, y equals 3x plus 2, and I'm looking for the domain, well, it's going to be a set of values x such that x is all real numbers. And the reason why I say that is when I'm looking at it from an equation standpoint,
I'm going to be looking for values that are going to cause a problem. Well, as I think about it, I can put in any number greater than 0. Any bigger number is going to work. It doesn't matter if it's 1, 1,000, 1 million, 1 trillion, doesn't matter. And same thing if I look at the negative numbers. If I go negative, it doesn't matter how large from a negative standpoint those numbers get. It's still going to work in this equation. The other number we want to check is like 0. If I put 0 in there, I don't have a problem either. So there's no number that I would plug in for x that would cause a problem or make that function undefined. So it would be all real numbers. Okay? And then the same thing would apply for y. The values that would come out of that function, well, I can get any number out of that. So this would also be all real numbers. And I used an abbreviation for real. Sometimes you'll see me do that where I use 2 slashes and make an R out of it like that. That just stands for real numbers. Okay. Number 2 then, if I'm looking at the domain, what numbers I can put in. Well, here's one where I have to be careful because this bottom number, I know on a fraction I can't have 0 on bottom. So if I look at x squared, I know that x squared can't be equal to 0. In other words, x cannot be 0. So my domain is going to be all reals that are not equal to 0. And my range, same thing applies. I can't get a 0 out of that. If this fraction can never be 0, if that fraction can never be 0, that means this number right here can never be 0. Therefore, the number that this function could never be equal to, or the value of y that we could never get, is I can never get 1. Because I'm always going to be adding or subtracting some number from 1 that is not 0. Therefore, y could never be equal to 1. So my range here is the values of y that are all real numbers, not equal to 1. Okay, so this is the notes for 1.5 using graphs and tables of functions. You should have already read section 1.5 in your book. If you haven't, you might want to just pause the video at this time, go back, make sure that you've read that section. I'm going to start out right away with an example problem here. It says the following. It says the graph below gives the distances Maria traveled during a 7-hour trip. She drove some, then visited a historical museum. After visiting the museum, Maria drove some more and then stopped for dinner before returning home. Which variable is a function of the other variable? Express this relationship in f of x notation. Which variable is a function of the other variable? Remember, it's dependent is a function of independent. So that the answer to that first part of that question is we have to figure out which one's dependent upon the other. Well, distance is dependent upon time. Therefore, d is a function of t, or distance is a function of time. Okay? Then it says express this relationship in f of x notation. Well, what we can then say is f of t is equal to the distance. Part B says state the domain and range. Well, the domain, remember, is the values that you can have for your independent variable. Or from a graphical standpoint, it's going to be the values of the horizontal. Okay? Well, we know, if we're thinking about this just from a word standpoint, it says Maria traveled on a 7-hour trip. Okay? So if you think about the values, we can't put in a value of 8 for time because she's only been on a trip for 7 hours. So the values for our domain are from 0, or from no time at all the way up to 7 hours. Now we can also see this graphically along our x-axis. That's the possible values of, in t-axis, that's the possible values of t. So when we state our domain is the values of t from 0 is less than or equal to t is less than or equal to 7. The range is the values of d, the distance, and the distance traveled. Well, although our graph goes up to 150 in terms of the way we have it broken up here, the highest that the actual curve goes is right here at 100. And so it goes from 0 to 100, so our domain, or excuse me, our range is from 0 is less than or equal to, in this case, d, to 100. Part C says estimate Maria's distance from home after 3.5 hours and write your answer using f of x notation. Okay? So when I look at 3.5 hours, it's right here on my t-axis. I'm going to look at the value of the function there, so I'm looking at where that would be. And we have 50, we have 75, and we have 100. It looks like it's about, part way between 75 and 100, and we're estimating here. So when we do that, I'm going to write it like this. I'm going to say f of 3.5 hours, so my t-value is 3.5, is equal to somewhere, looks like, I'm just guessing, but I'm going to go with, say, about 85 miles. So after 3.5 hours, she's about 85 miles from home. Okay. Part D says estimate how much time it took Maria to first be 100 miles from home. So once again, let's look at this, and let's see if we can figure out when is she going to be 100 miles from home. Okay. Well, here's the 100 miles, right? So if that's 100 miles right there, and we're looking at when is she first there, well, that looks like that is occurring right there, which is at about 4 hours. So the answer here would be 4 hours. All right, finally part E says, what is the significance of the left horizontal line segment and estimate its endpoints? Well, if you look at the graph, there are two parts of the graph that are horizontal. There's this part right here, and there's this part right here. Okay. Well, the left one would be this one right here. And what we want to know is, says, what is the significance of this? Well, the left horizontal line would be what would occur first from a time standpoint. And according to the problem, it says the graph below gives the distance Maria traveled in 7 hours. She drove some, then visited a historical museum. So the first stop that she makes is at a historical museum. Well, when she stops, she's not moving forward, therefore that would be a horizontal line graphically, because she's basically standing still in terms of her distance, so she wouldn't be going up at all in terms of distance. So that first horizontal line would represent that she visited historical museum. And then the second piece of that problem says estimate its endpoint. So I want to know what this point right here is and what this point right here is in terms of ordered pairs. So it looks like the left endpoint would have to be at 1.5 hours, and it looks like the museum was at about 75 miles, so it'd be at, the left one would be at 1.575, and the right one, where she ended her museum stop, was at 3 hours, so that would be 3, and also at 75. So those represent the endpoints of that horizontal line segment. So at this time, what I'd like you to do is just take a few minutes to go through guided example number 1, and I'd like you to answer each of the questions that they have there. You'll notice that guided example 1 is very similar to the one I just did. Get your answers for that, and do that while you have the video paused. When you're done, turn the video back on, and I'll go through the answers so you can see how you did on that. Take a look, make sure that that's what you had as well. It should be something close to that now, like part C there's some estimation, etc., but for the most part you should have those answers. If you have any questions, make sure you ask about them in class. Next time we can talk a little bit more about that. Okay, the last thing I'd like to do in these 1-5 notes is to take a look at example 2. Example 2 says Robert Wadlow is the tallest person in medical history whose height has been substantiated. At birth, he was of normal height. The table below gives his height h at various ages a, where h is equal to f of a. Part A says, what is the domain of the function defined by this table? Now, a key component to this is it's asking defined by this table. So we're only interested in those values within the table. So as I look at that, the values that would be the domain are the first row of the table. Therefore, and we also know that age, A, is the independent variable. Therefore, the values that would be the domain are these values right here, which I have listed along the way as well. Part B says, what is the range of the function? Same idea. We're defining it by the table. Therefore, the range is going to be the second row, or the height of Robert. So it would be just those values based on the table. Okay. Part C says, find f of 16. Well, f of 16, that means that instead of a, I'm looking at 16. So his age is at 16 years. And at 16 years of age, he was 2.4 meters high. So it represents his height at 16. And the value is 2.4 meters. Part D says, for what value of a does f of a equal 2.7? So when we're doing that, now we're looking for the value of its height, the value of the age when we know the height is 2.7. Remember that f of a equal to 2.7 is like saying h is equal to 2.7. Therefore, at 2.7 a height, the age was 22. So a would have to be 22. Okay, these are the notes for section 1.6 solving equations. You should have read section 1.6 already before doing these. Primarily what we're going to do is we're going to look at a few examples here. Solving equations is something you spend a lot of time on in your first algebra course. Just a reminder, when we're solving an equation, any sort of a linear equation meaning that it forms a line if we were to graph it, when we're solving that, what we're going to do is we're going to work our way backwards through our order of operations. Okay? So when we're solving an equation, really what we're doing is we're undoing what has been done to the independent variable. So let's take a look at this first example. It says, in the board game Monopoly, you purchase 4 houses and a hotel on Illinois Avenue for a one-time cost of $750. You will earn rent of $1,100 each time another player lands on the property. If I players land on Illinois Avenue, then your profit is f of I is equal to 1,100I minus 750. What is your profit after one player lands on Illinois Avenue? Well, really what we're doing here is we're evaluating that function when I is 1. So I'm going to put 1 in for I. So f of 1 is 1,100 times 1 minus 750, which would be $350. So that means that the profit would be $350. Okay. Part B says, how many players must land at Illinois Avenue so that the profit is at least $15,000? So now what I'm doing is I'm solving this equation, this function, for when the function's value is 15,000. Okay? So I'm plugging 15,000 in for f of I. So I have 15,000 is equal to 1,100I minus 750, and now I'm going to go through and solve that. So I have to, what I'm trying to do is I'm trying to get I by itself. So I'm going to undo what's been done to I. Well, if you think about what's been done to I, we're multiplying it by 1,100, and we're subtracting 750. So when I when I solve the equation, I said I'm going to go backwards through the order of operations. So the last thing in my order of operations is addition or subtraction. So the first thing that I'm going to undo is addition or subtraction. So in this case, I'm going to undo the minus 750 by adding 750 to both sides, which gives me this. And then I'm going to undo the multiplication by dividing both sides by 1100. That gives me a little over 14 times, but it wants to know in such a way that your profit is at least 15,000. Therefore, the number of times would have to be 15 that a person would land on that. Okay, another review topic from Algebra 1 is the idea of the distributive property. By definition, the distributive property just says for all real numbers a, b, and c, if I take c times the quantity a plus b being in parentheses, then that's the same as c times a plus c times b. We distribute the c to both or all of the values that are being added or subtracted inside of parentheses. That's what the distributive property tells us. Here's an example of the distributive property. Okay, notice how I've multiplied negative 3 times each of the terms that is inside the parentheses. Okay, so let's take a look at number 2, where we have to utilize the distributive property in part to solve this. It says, suppose you just received $50,000 inheritance. At first, you decide to invest some of the money in a certificate of deposit account that earns 6%. The rest of the money is in a savings account that earns 4%. If X dollars are invested at 6%, then E of X is equal to 0.06X plus 0.04 times 50,000 minus X would give you the interest earned in 1 year. If you want to earn $2,500 in the first year, how much money should be placed in each account? Okay. So what I'm going to do is I'm going to set, because I want my interest to be equal to, after 1 year, the value, in other words, the value of e to x, to be equal to 2,500. I'm going to set 2,500. I'm going to replace e of x with 2,500. Okay. Now I'm going to solve this. Well, the first thing I'm going to do in my solving process is I'm going to use that distributive property, because if I distribute that through, that will allow me to combine my like terms of x's, my 0.06x and my negative 0.04x, to get this. Now I can go through and think about, okay, my order of operations. Well, the last thing that's being done to x is I'm adding 2,000. So the first thing I'm going to undo is I'm going to subtract 2,000. So right here I'm subtracting 2,000 from both sides. Then I'm dividing both sides by 0.02 to get my value of x, which would be 25,000. So in other words, they would have to put $25,000 into the account that earns 6%. Okay, another method that we use to help us in solving equations is the idea of clearing fractions. This is something that we use for simplicity. It's not something that we have to do, but we can do it by multiplying both sides of an equation by a common multiple of the denominator. So anytime we have fractions throughout our equation and we want to kind of eliminate fractions as a possibility, we can do it just by multiplying both sides of the equation by the same number, which would be a common multiple of their denominators. Okay? Well, let's take a look at this example in which we're going to use clearing fractions to help us solve it. It also is an example of taking a word problem and write an equation out of it, something you spent some time with in Algebra 1. It says, suppose during the 07-08 regular season NBA game involving the Boston Celtics, Kevin Garnett scored 1/3 of Boston's points in the game. Ray Allen scored 1/4 of the points. The rest of the players scored 60 points. Write an equation to model the situation, then determine how many points Boston scored in this game. Okay. Well, I have highlighted here how many points Boston scored in this game. The reason why I did that is because that's what I'm trying to find, so that's what I'm going to let my variable equal. Okay. So if I let x equal the total points scored in the game, then I can say the total points scored in the game, x, is equal to, well, 1/3 of them were scored by Kevin Garnett. So this is Kevin Garnett's share. 1/4 of them was scored by Ray Allen. So this is Ray Allen's share of the points. And this 60 represents all the other players and what they scored. Okay, so now I have an equation in which I only have one variable x. Well, sometimes it's just not fun to deal with those fractions, so we're going to get rid of those fractions. And if I look at 3 and 4, they have a common multiple of 12, so I'm going to multiply through the whole equation, both sides, by 12. If I do that, I get 12x is equal to 4x plus 3x plus 720. Okay, so now I'm going to go through and do the solving by combining like terms first. So 4x and 3x is 7x. I'm going to get my x's together by subtracting 7x from both sides. That's where I'm getting the 5x equals 720. Now if I want to get x by itself, I need to divide both sides by 5, which is going to give me x is equal to 144. Therefore, that game, they scored 144 points. Okay, the last theorem that we have here is what we call the opposite sum theorem. And it says for all real numbers a and b, the opposite of the quantity a plus b, in other words, negative the quantity a plus b, is equal to negative a plus negative b, okay, or negative a minus b. What that tells us is when you have that negative outside of the parentheses, you need to distribute it to everything inside the parentheses. Here's another example of that, negative the quantity 2x minus 9. I'm going to take the negative 2x and the negative times the minus 9, which gives me plus 9. Okay? So let's use that. We're going to use that in this particular example here. It says, so we're right here, and it says h of y is equal to 13y minus the quantity 26 minus 3y. Okay? So if I'm going to solve that for when the function is equal to 100, I'm going to take h of y out and put 100 in. Okay? At the same time when I do that, I'm going to distribute this minus to both of these to get rid of those parentheses. And by doing it, I get 13y minus 26 plus 3y. Okay? Now I'm going to combine my y's to get this. I'm going to add 26 to both sides to get 126 is equal to 16y. And then if I divide both sides by 16, I get 63 over 8, or 7.875. So that would be the value of y when h of y is 100. Okay, this is the notes for section 1.7, rewriting formulas. You should have already read this section before starting to go through this video and take your notes on this. What we're looking at here is taking formulas and solving them for any one of the variables within the formula. Every formula defines one variable in terms of the other variables, and by using equation solving properties, or things that we've used in terms of solving equations in any algebra equation really, you can manipulate a formula such that you can solve it for one of the variable in terms of the rest of the variables. So what I'd like to do now is I'd like to go through a few examples of how we would go about doing that. So here's example 1. It says the period p of a pendulum is the time in seconds that it takes a pendulum to make one complete swing back and forth, and is calculated by using the formula p equals 2 pi times the square root of L over g, where L is the length of the pendulum in meters and g is the acceleration due to gravity, which will always be 9.8 meters per second squared. So part A asks us to solve this for L. So basically what we want to do is get L by itself, and we can only do that by undoing everything that's been done to L. Well, if you look at what's being done to L, we're dividing it by g, we're taking the square root of it, and we're multiplying it by 2 pi. Okay, so the first thing I'm going to do is I'm going to get rid of that square root symbol. Kind of works as a grouping symbol, so I'm going to get rid of the stuff outside of that grouping symbol by dividing both sides by 2 pi. Now if I do that, if I divide both sides by 2 pi, this is what I get. Okay, p over 2 pi. These 2 pi's will cancel out, so I just have the square root of L over G is equal to p over 2 pi. Now to get L by itself, I need to get rid of the square root. So what I do is I square both sides. Well, when I square the left-hand side here, I have to square everything. So I get p squared, I get a 4, I get a pi squared. Okay, and then this just becomes L over G. Now, if I want to get L by itself, the only thing left is to get rid of this division. Well, if I'm going to get rid of dividing by G, I'm going to do the inverse operation, which is to multiply by G. So I'm going to multiply both sides by G. Well, G is like G over 1, so when I take P squared over 4 pi squared times G, that's like putting the G on top with P squared. So it'd be P squared G over 4 pi squared is equal to L, and now we've solved it for L. We've done exactly what we wanted to do, and that was get L by itself. Okay. Part B says, what is the approximate length of the pendulum whose period is 1 minute? Well, if its period is 1 minute, remember P stands for the length of time in seconds. Okay. Therefore, I can't put 1 in for P. I need to put 60 in for P. So I'm going to plug 60 in for P. We know that G, we said, was 9.8 meters per second squared, so I'm going to plug that in. And then I have over 4 pi squared. Remember, pi is a number, so when we go to calculate that, we're going to use that pi key in our calculator. So if I plug this into my calculator, it gives me a number that is very close to 894 meters. Okay, example 2 here. Before we do that, let's talk about what it means for formulas to be equivalent. Formulas are equivalent when the values of the variables that satisfy them are the same. So if you look at what we did in example 1, it didn't matter if we had solved that for L or we had solved it for any one of those variables. If we solve it correctly, those are equivalent formulas. Okay. So if I look at number 2 here, we're going to apply that same idea here as well. It says, because the density of air consumed by scuba divers increases as they dive deeper, they consume more air the deeper they dive. The formula T equals 30s over D plus 30 is used by some scuba divers to estimate the number of minutes T of air they will have at a depth D in seawater. If they consume a tank of air at the surface in S minutes, solve the formula for D in terms of T and S. Well, when we say in terms of T and S, that means that T and S would be the independent variables for the dependent variable D. So what I'm going to do is I'm going to undo everything that was done to D. So if you look at D, we're adding 30 to it, and then we're taking that and dividing 30s by it. So we have a unique problem that we have the variable that we're looking for is on the bottom of the equation. So we have to do something about that. So I have to get this D off the bottom of this fraction. And the way that I do that is by multiplying both sides by this denominator. If I multiply both sides of this equation by D plus 30, what happens is on the right-hand side, my D plus 30s cancel out. So I'm left with just 30s. And over here on the left-hand side, I have D plus 30 times T is equal to 30s. So this is what we get right here after we've multiplied both sides by D plus 30. Okay. Now, once again, we want to focus on we're trying to figure out what D is, so that's what we're trying to get by itself. Well, there's no sense in distributing this T through to both of these using the distributive property, because eventually I want to get rid of it anyway. So the best way to do that, since I'm multiplying T times this stuff, I can divide this whole side by T. Now, if I do that,
I have to divide the other side by t as well. So these t's will cancel out, and I'm left with d plus 30 is equal to 30s over t. And now we're real close. We just got to get rid of this plus 30, and the way that we can do that is by subtracting 30 from both sides. And if I subtract 30 from both sides, I'll get what d is, which is 30s over t minus 30. Okay, in example 3, we're going to look at using your CAS calculator to help you solve a formula for a particular variable. If you look at number 3, it says a certain ancient pyramid has a volume of x cubic meters. Each side of its base is 231 meters. Part A says solve volume equals 1/3 base times height for h. Okay, so let's go through and look at how we can do that on our CAS calculator. So you might want to get your CAS calculator out at this time as well, so you can kind of work along with this as I go through it. So I start just by entering this into my calculator. Remember, to get 1/3, you can hit Control and divided by to get that fraction. Now I'm going to think about exactly the way I've done it by hand. If I'm going to go about getting h by itself, I've got to undo what's being done to it. So I'm going to get rid of this 3 by multiplying both sides by 3. And the way that I do that on my calculator is I'm just going to put multiply. Notice how it brings up a and s like that, by 3. Oops, 3. And hit enter. And now you'll notice that it eliminated the 3 on the right hand side and brought it over to the left hand side. Now I also need to get rid of the b by dividing by b if we're going to have this solved for height. So I'm going to hit divided by, it brings up a and s again, by b, hit enter, and we have 3v over b is equal to h. Now, one thing you have to be careful about when you enter your formula at the beginning, you can't put 1/3 bh, because it's going to take bh as being one variable. So you have to say times b times h. Otherwise, you're not going to be able to actually solve this on your CAS for h. So this right here would be the value of that formula that's solved for h. Okay, part B says assume that the pyramid has a volume of 2,614,689 cubic meters. What is its height? Well, to find its height, I need to know two things based on what we found in part A. I need to know what is the volume, which they just gave us. And I also need to know B, which, remember, is the area of the base of that pyramid. So if I know those two things, I can plug them in to solve for height. Well, I know the volume, and I also know from the first part of our problem that the base, each side of the base, is 231 square meters. Therefore, the base must be a square. So when I look at B, B is going to be equal to 231 squared. So now what I can do is I can plug those two things in to my calculator, into the formula that we had before, and solve for h. So if we go to our calculator and we plug that in, 147. Therefore, the height of that pyramid, h, would be equal to 147 meters.
Okay, this is the notes for section 1.8, explicit formulas for sequences. If you haven't done so already, make sure that you've read 1.8. If you haven't, go ahead and stop the video, read it, and then go ahead and start it again. First of all, we're going to look at some terms. The term sequence. What is a sequence? Well, really a sequence is a function. It's just a special type of function. And the special type of function that it is that its domain is a set of positive integers, or the set of positive integers from a to b. In other words, it's either positive integers starting with 1, 1, 2, 3, 4, etc. on forever. Or it could be just a set of positive integers, say from 1 to 10, or from 6 to 8, or from 12 to 24. So it's always going to be whole positive numbers in terms of the domain. The range could be anything, but the domain has to be positive integers. Okay? The term in a sequence is an item or element in a sequence. Really, the term, the value of a term is the dependent variable in the sequence, whereas the independent variable or the domain of that sequence is the positive integers. So the term number is the domain, the actual term is the range. Okay? Now, the next thing we have, and this is something we'll be using quite a bit throughout the year actually, is the idea of a subscript. And a subscript is a label that is set lower and smaller than the regular text. For example, T and then a little 3 below. That 3 is the subscript and is read T sub 3. So anytime we read a subscript number, we'll say sub and then that number. So T sub 3, M sub N, X sub 3, or X sub 5, anything like that. Okay? Finally, in terms of terminology that we have, under the idea of writing explicit formulas for sequences, explicit formula for the nth term of a sequence is a formula that describes any term in a sequence in terms of its term number. Okay, well, it's kind of hard to understand. First of all, realize that we're talking about an explicit formula. We'll talk about a different type of formula for a sequence later in this course. But an explicit formula for a sequence is when you can write a formula in terms of the term number. So in other words, our domain is the term number. Okay, let's look at the first example that you have in your notes there. It says, consider the formula T sub n equal to 3 raised to the n power minus 4. Assuming n is greater than or equal to 1, what are the first 4 numbers in the sequence defined by this formula? Okay, so n, remember, is your term number. So if I'm finding the first 4 numbers in that sequence, I'm looking for the first term, the second term, the third term, and the fourth term. So in other words, I'm looking for the value of the sequence when n is 1, 2, 3, and 4. So T sub 1 is when n is 1. So I'm going to put into that function 1 for n. And if I do that, I would have 3 minus 4, which is negative 1. If I'm looking at the second term, n is 2, so I have 3 squared minus 4, which is 5. For the third term, n is 3, which will give me 23. And finally, for the fourth term, when n is 4, I would end up with 77. And then for part B, it says evaluate T sub 10 and explain what it means. Well, T sub 10 is the value of the function when n is 10. Okay? In other words, it's the value of the 10th term within that sequence. And if I do that, if I plug 10 into my sequence, 3 to the 10th minus 4 is 59,045. So that would represent the value of that sequence for the 10th term. All right, let's take a look at example 2 now. If we're going to in this example we're using explicit formulas for sequence. It says Alfonso has invested $750 for 1 year at 8% annual interest. If we use the sequence a sub t is equal to 750 times 1.04 raised to the 2t, that represents the value of that money after any given number of years. Okay, so t is equal to the number of years that money's been invested. So if you look at that formula, it makes a sequence based on years. Okay, so it says if the interest is compounded semi-annually, how much will he have at the end of 1 year? Okay, so if that's the case, that would be the value of the sequence at a sub 1. So we're going to say 750 times 1.04 raised to the 2 times 1, because t is 1. Well, if I do that, I could plug that into my calculator, you'll find that that's $811.20. Okay. For part B, it says how much money will Alfonso have at the end of the second and third years, assuming no withdrawals. Okay. Well, everything is exactly the same as in part A. The only difference is now I'm finding the second and third terms instead of the first terms. So instead of 1, I'm going to put 2 in for t, and instead of 1, I'm going to put 3 into t for the third term. Okay. And you can see the values then of that money after 2 years being $877.40, and after 3 years $949. Now each of those I'm rounding to the nearest cent. Okay, and then finally part C says how much money will he have after 10 years, assuming no withdrawals. Okay, well that would be a sub 10, or the 10th term within the sequence. Okay, so I'm going to plug 10 in for t, and if I do that, I would get $1,643.34. All of this whole problem is, if we're doing this as a sequence, remember that t, the time, is limited to years. So what that's saying basically is you can't look at what is the value after 1.5 years. We're only looking at it at the first year, the second year, the third year, etc., on down the line, every year on its anniversary. Okay, if you could pause the video at this time and just complete guided example number 2 from page 56. Once you're done with that, go ahead and start the video again, and I'll put the answers on here for you to see. Okay, here are the answers to solution number 1. Take a look at yours and see if they match these. If you have any questions, make sure you ask about those in class next time we meet. Okay, so here's the solutions for solution 2. So we want to do that on our CAS. So what I'm going to do is I'm going to come over to my CAS, and first of all I need to define the function s sub n, which I have here. And then I'm going to add a lists and spreadsheets, this one right here, okay, which I've already done. And when I do it, it's going to bring up a blank one of these. You're going to put n up here, and then you want to put the values from 1 to 5. And then right here, you're going to put in s sub n. And when you do that, I'm going to show you what's going to happen there. If I just put in s sub n, it's going to ask me if I want to do column reference or variable reference. So basically it's asking me, do I want these letters to be n, or do I want it to be this variable n? And the answer is I'm looking for the variable reference, so I'm just going to say that, and then it's going to go ahead and plug those numbers in correctly. So here's those values then, which you can see is exactly the same. And then if I want to find the 100th value, I can just put 100 right here, and it will give me that value of the 100th term. I can expand this out as well, so we can see that. Remember, e to the 6th, or e6, that means that I need to move my decimal place over 6 places to get the actual value of that. Okay, so that would represent the value of the function at 100. So there's the final solutions to the guided example.